Oh, oh. What about here? Maybe we did this. Okay. So looking at this, you're starting to realize. Uh-oh. Wow, that's slow. Looking at this, you're starting to realize the way the periodic table's set up that we can actually, just look at the periodic table to go across and figure out electron configurations, right? We know that S's are filled over here in the green, and then the transition metals is my D, P on the right, and then F is down below with the lanthanide and actinides here. You just kind of follow the atomic numbers across. When the periodic table tells you to go from, here down to here, you do that. Just follow the atomic numbers. So these are the electron configurations for a couple alkali metals. So this is group 1. And you notice they have the same number of valence electrons. This one valence electron. And that is some of the reasoning behind why things behave similarly, right? Same electron configuration. Even though the nucleus is different and the core electrons are different, that doesn't play out that much in chemical reactions and chemical properties, so that you see similarities between these. It does have some impact, and that's why you see differences. But as far as chemical reactions, I mean, it's valence electrons, and that's why these all form, chlorides, compounds. So these types of things you start to see. Now, as we went through some of the filling and learned how to do these electron configurations here, it's not all so nice and tidy. There are some exceptions to the way things fill. And 2 examples are right here. So looking at chromium, which of course is your first row of your transition metals, group 4 there, period 4. And what you would expect is everything through argon, right? We can use the condensed form, so everything through argon, and then 3d4, 4s2. That's what you would expect. These 2 are filled, and then 1, 2, 3, 4. There's chromium. That's what you would expect. However, this is what you see. So Megan had asked the question in the last class, how do they detect electrons and all of that? And question caught me off guard, but when I thought more about it and I did a little reading, I realized you detect it the same way you detect anything with electromagnetic radiation. You just have to use a low enough frequency. So you can detect it. They use these stuff that's way beyond me, these cloud chambers and things like this. But you can do different types of X-rays and stuff like that to determine the electron position. You can actually do things similar to Rutherford with screens that show where it shows up, and also you can use magnetic fields to bend its path, and then for back calculate through velocities and trajectories the origin of the electron. So you could do some interesting stuff. Most of it's well beyond me, anything I've ever done, but it is very doable in terms of figuring out where an electron is and which orbital and that type of thing. You can't identify its exact location, okay, pinpoint it, but the more accurate you get, the less you're able to know about its velocity. That's the Heisenberg uncertainty principle. If you know the position, you can't know the momentum at the same time. So the more accurate you try to pinpoint its location, the less you know about its momentum. All right, so we know what we observe experimentally to be 3d5, 4s1. Turns out that, remember what I told you, everything's the result of lower state of energy. It turns out having all 5 of those d orbitals filled with spins in all the same direction is a lower state of energy than having the 2 in the s and having only 4 d electrons in those. Because remember, there's only 5 d orbitals. So by filling them all with 1 electron, that somehow lowers the energy. Okay, that's about all I can tell you. I mean, That's about all I know. And Richard Feynman, I've quoted him before. He's famous for saying that if I try to explain it in terms that you understand by comparing it to something, well, I can't do that, he says, because there's no way to do that. The only way to explain it is your level of understanding. And this is it for here. Okay, it's just a lower state of energy. Okay, now maybe when you take physics and physical chemistry, they might go into that. I'm not even sure we know that. I'm not positive whether or not we know why 5 electrons all occupying the d orbital spinning all in the same direction is a lower state of energy. But there's probably people out there that are doing stuff like this and maybe have answers to those questions. I just not something I've looked into recently. But let's just go with that. It's a lower state of energy. Now you see the same thing if you go over to something like copper. When you have the opportunity to have only 1 electron missing from D, that's not particularly stable as opposed to having only 1 missing from S and filling all of those D. Because remember, that D is a lower principal quantum number anyway. Okay, so what you'll see is when we form ions, we'll start to see that makes sense, because when these things form ions, they lose electrons from the higher principal quantum number first. So they'll lose from that 4s before they lose from the 3d, even though it fills the opposite direction. Okay. And part of it, you can think of it as, well, you know, S only needs 2 electrons. So if I start filling that first, I can fill that shell. And when you can think of that as when the shell is filled, it kind of like lowers its energy state. Okay. So, hey, I could quickly fill 4s with 2 electrons. It's going to take me 10 to fill 5, or 10 to fill D, or 5 to fill it halfway at least. Okay. So, these deviations can occur for other row elements as well. So you'll see it for molybdenum, which is right underneath chromium. You'll see it for silver. You'll see it for gold. Gold is AU, silver is AG, molybdenum's MO. However, tungsten doesn't exhibit this characteristic. And don't ask me why. It's probably something to do with a balance of effective nuclear charge and shielding, that it's just not the same and correct as I move over. In the periodic table, you see it happen with gold, but you don't see it happen with tungsten. But gold's got a larger nucleus, therefore it's got a different effective nuclear charge. So everything changes with each additional proton added, neutrons added to the nucleus, and electrons added. So there's so many variables here. Say that again.
So, like your expected configuration, you write the D central before the S central.
Well, so I'm not sure I understand your question, but let me say something first, and I'll see if I answer. First of all, there's 2 ways to write these configurations. Some people will write it 4s2 3d4 because that's the way it fills. The more common convention, which is what your book uses, is to write with the lower principal quantum number first, even though the 4s fills first. Because you look at the periodic table, what I'm going to do is go 4s. Let me erase this. It's such a mess. Oh, so this was done the other day, so it won't erase unless I do it on PowerPoint. Anyway, so what you're going to see is 4s1, 4s2, 3d1, 2, 3, 4. So the 4s fills first, and that's basically just the Aufbau principle. This is the energy levels. When you do the quantum mechanical calculations, the 4s turns out to be lower energy than 3d. Okay, so it fills first, even though people write it typically like this. Okay, does that answer your question? It is. Some people do it that way. In fact, I think that's the way I learned it, because it makes sense to, as you're going across the periodic table, to write it first. this is the more standard convention. I'll stick with this because this is what the book does. This is what smart work does, and that's what your exam will do. So just be comfortable with either way if that's the case. If you like to do it the other way. So there, once again, there's so many variables and so many things going on. But what's nice is that we can start to explain some of this stuff, and I'll show you that through some of the trends we'll look at in a second. But why tungsten doesn't do it exactly, I don't know. I'm not positive. Questions?
So for both of those, the ending numbers for like a number and then one, would those follow the same pattern? Like does gold only have S1 and
Yes.
Okay.
Yes, just you know, you've got a different quantum number, so you'll be down lower. So, you know, for gold, you're 2 more down under copper, so it'd be, you know, 5d10 6s1. But that's right. And keep in mind that these numbers are the numbers of electrons. So to check yourself when you're doing the electron configuration, they need to all add up to the number of electrons. So if you look at chromium, chromium has 24 electrons. So you better add up to 24 when you're done with your configuration. And you look at argon's got 18. Okay, 18 and 5 and 1 is 6. You have 24. That's a good check to make sure you haven't missed something or forgotten something. Okay, you could still mess up, you know, your orbitals and all that, but still, those superscripts are the number of electrons. So they need to add up to whatever your atomic number is. Other questions? Yes.
how are we supposed to know if it's like we said that expected, we expect that one. How are we supposed to know like which ones should be the
You just need to memorize a few of them.
memorize them?
Yeah. So you should now know that chromium, molybdenum, copper, silver, and gold are exceptions to the normal filling order. Yeah, other than that, there's no way for you to predict that. I mean, now theoretically there is, because I've told you why it happens that D being half filled or fully filled is lower energy than S being fully filled. But there's only a couple places this happens, and this is it. And I've told you. And there's a couple that happen also with the F, but you're not responsible for those. You'll see the same type of thing happen down here when you're filling these. We've got the opportunity to have all the F half filled, all the F fully filled. But I'm not holding you responsible for that. But as you learn the material and you go forward and you see that in the future, you'll say, oh yeah, I remember that we talked about that. There's another one, there's acceptance. Or you're doing smart work or whatever. That you realize that. Okay, now. Yeah, no. Yeah, it's the ones right underneath the ones we did on the periodic table. So under chromium, you've got molybdenum, not tungsten though, which is W. And under copper, you've got silver and gold. But it doesn't happen when you get down further. So, and you can look, you've got all the electron configurations available to you. They're in the book somewhere. I think they're in an appendix or something. So you can just look and just see what the electron configuration is. So keep that in mind as you take your exam. What I'm not going to ask you is, what's the electron configuration of phosphorus? Because you can turn to your book and look it up. So the questions are going to be structured in a way that's very different than that. All right. So looking at now ions, it makes sense now that you've covered quantum theory that in electron configurations, why sodium loses an electron and why chlorine, or fluorine in this case, picks up an electron. Well, look at it. Sodium's got one beyond a noble gas configuration. We think of the noble gas configuration as being stable. So it loses that one electron and it now has the same configuration as neon. Okay? Still got the 11 protons, so it's still sodium, but it has the same electron configuration as neon. And now look at fluorine. Picks up one electron, it's got this stable octet. It's got the configuration of neon. So sodium cation and the fluorine anion are isoelectronic. They have the exact same electron configuration, and they're isoelectronic with neon. So those three have the same electron configuration. So we say they're isoelectronic. That's a term you should know. Does that make sense? Why they lose or gain those electrons and what isoelectronic means. Okay. Now, these are the transition metals, and this is how they lose electrons. Nickel loses 2 electrons. Lo and behold, it loses them from a higher principal quantum number. It loses the 2 4s ones. Because when you think about it, it's like, well, losing 2 from the D doesn't accomplish much. You still have 6 there. Okay. But hey, if I lose 2 from the S, maybe somehow that, I don't know, I can just, make stuff up. Yeah, somehow that's more stable. It obviously is. I just don't know why. Why, losing those 2 is more stable than losing 2 from D. Titanium loses 4 electrons, and it loses obviously the 2 from the S and then the 2 from the D. If it was titanium 2 plus, it would lose those 2 from the S first and then the 2 from the D, because there is different charges for these elements. Nickel is almost exclusively +2, but titanium is also 2 plus, not just 4 plus. And you should be familiar with iron now. Iron is +2 and +3. We'll see that in chapter 4 when we do some naming. Questions? Okay, write the condensed electron configuration for each of the following. So magnesium loses 2 electrons. What's its noble gas configuration going to be? Neon, it's going to lose, it's got 12, it's going to lose 2, it's got 10. So for magnesium 2 plus, we basically wind up with neon. What about chloride -1? Argon, right? It has 1 electron. What about calcium 2 plus? Right, calcium 2 plus is also argon, so those are isoelectronic. How about O2 minus? Neon. Which ions in part A are isoelectronic with neon? So we've answered that already. Those are isoelectronic with neon. Okay. Sizes of atoms. Now, what do you think? Do the atoms get larger or smaller as you move down the periodic table? Larger. You're adding energy levels, right? That's not rocket science. Okay. However, how about as I go left to right? Smaller? Why? Very good. The effective nuclear charge, the pull of the nucleus. Think of it like a magnet. As I move across, I'm not really adding any new energy levels. I'm adding sublevels, right? But those aren't really the size. N dictates more of the size. It's almost like you're adding stuff within that energy level. But my nucleus is getting larger and larger, right? So it's like a bigger magnet. More protons pulling in the electrons in those outer shells closer, making it a little bit smaller. The effect going down is much bigger, better, much larger. Actually, it's not that much different. Actually, it's quite substantial. The decrease in size as you move across, surprisingly so. Here you see it. So I guess maybe going down is a little bit more significant than going across, but it's still pretty significant. Moving across in size. These are measured in picometers, I believe. or is it? It's either angstroms or picometers. It's probably pico. That's got to be picometers. 110 picometers. Yeah. So picometers. And you see the size trends. This is pretty basic. There's not much to it. So an exam question would be, arrange these in order of increasing size or decreasing size. I can throw ions in there too, though. Let's hang on to that thought for a second. This is the explanation. We've kind of already talked about this. Okay? So there's any questions on this? So it decreases as you go across. It's what we said, effective nuclear charge. Okay? Now, a cation will be smaller or bigger than its parent atom. Smaller. It's losing electrons. Now remember, electrons repel each other. So the electrons in the shells are actually repelling each other, and they can actually increase in size. So in some cases, it's just a repulsion effect. In other cases, you're right, it might actually be losing a whole energy level, right? So with something like the alkali metals and the alkaline earth metals, they're losing entire energy levels, right? Calcium loses 2 electrons. It's lost the 4th energy level. There's nothing in it anymore. And it's down to the argon gas configuration. But something like in the middle of the periodic table, like iron, that loses 2 electrons, well, it loses 2 from that S, right? That makes sense that it's smaller, okay? But sometimes they don't always lose. Let's see. No, those are all going to lose the S. That's right. So a +1. So like silver's going to lose the 1 from the S2. That's right. So maybe, no, they're all going to either, yeah, there's going to be no S left for a cation in the transition metals. Not sure about the lanthanide and actinide series. There might be some exceptions there. Anyway, I'm just kind of thinking out loud. So in general, a cation's losing an energy level and is going to be smaller than the parent atom. Anions are gaining electrons. In that case, like something like chlorine, it's not really adding an energy level, just adding an extra electron. But if you look at it, it's quite a bit bigger. Look at that. That's pretty darn big. So that's got to be all due to electron repulsions, right? And you can think of it like this too. That stabilizes because you're spreading out the electrons, so there's less repulsive forces. So this is why something like a halogen likes to pick up electrons. We say it gets more stable, but why does it get more stable? Well, it swells and stabilizes itself by spreading out those repulsive forces. And now you understand why halogens tend to form the -1 ions. They pick up an electron, they complete that octet that stabilizes them. And they're stabilized by the fact that, in one way at least, is that these repulsive forces are now reduced. Questions? Okay, ranking atoms and ions by size. Use only the periodic table. So we don't want to look at the numbers. We just want to do this logically. So A, we got oxygen, phosphorus, and sulfur. We want to arrange it largest to smallest. So which one's those the biggest? Phosphorus, right? Because it's further down and further left. Then what? And then, of course, we're left with, oxygen. So phosphorus is bigger than sulfur. Sulfur is bigger than oxygen. Now, sodium cation, sodium and potassium. Which one's the biggest? Potassium, right? It's down below sodium, and the cation's going to be smaller than the atom. So potassium's got to be first, and then sodium, and then the sodium cation. Okay. All right. Atomic size is not that difficult to understand. Okay. In terms of even atoms and ions, it's not conceptually challenging like some of the stuff we've done in this chapter. Ionization energy is a little bit more to think about. It's the energy required to remove an electron from an element. And it's measured a certain way. It's measured in a gas chamber. So it's in the gaseous state. That means things like lithium, they'll be in the gas phase, which means it's got to be high temperature, right? And you're usually measuring a mole. You're not just measuring one. You can't measure one atom. We can't deal with single atoms. We can't manipulate them like that. So we do a mole, and that's what the numbers are. And it's the energy required to remove electrons from atoms. So you tell me, what do you think the trend would be like? Which elements on the periodic table would give up their electrons the easiest? Which one? Biggest, and also to the left more, right? These are your metals that like to lose electrons, right? And the biggest ones. So what we see is it increases like this, and this, your book has it as decreasing down, which same thing. But I like to think of it as increasing up and over as far as ionization energy, which means fluorine, noble gases aside, fluorine's going to be the least likely to give up an electron. Why? Well, because it wants an electron, right? To complete its octet. It's also the smallest. So it's got the biggest pull on its electrons, and it's going to be the least likely to give one up. Okay? And of course, the noble gases will be even further the case. But as far as elements that actually form ions typically, now all of these we can get to form ions in a controlled environment in a gas chamber. Okay? We can do that. We can, no problem. We can get an electron off of fluorine, even though it wants an electron, because we're going to put the energy in to get that electron off. Now, what's great about quantum theory is we can start to explain these trends. You see this here? These blips, where it actually increases? It increases from lithium. Oh, wait, I'm sorry. It's supposed to increase. I'm sorry, the next one over. Oh, heck, I keep doing it. This one here decreases. And then the oxygen one is the one I wanted. And it decreases there. We can actually explain this by thinking about electron configurations. So, keep in mind that boron has one p electron. And beryllium, I'm comparing boron B to beryllium Be. Be has a full subshell. So it's pretty stable. It doesn't want to give up an electron. But boron has one p electron. So if it gives that up, it now has a full subshell in the S. So that's why it has a little bit less energy. See, to me, that's the be all nerded out here, but that's the beauty of it. Is that you can sit here and explain these trends in ionization energy because you understand electron configurations, which all comes from quantum theory. You can actually explain why we see this trend. Not only that, you can explain the deviations in the trend because you understand the electron configurations. Same thing over here. Oxygen has 3p, right? Oxygen has, nitrogen has 3 all spinning in the same direction in the p. Okay? So remember, we said that's kind of stable when we have half-filled orbitals. 3p all spinning in the same direction, 5d all spinning in the same direction, 7f all spinning in the same direction. Those are stable. Okay? They're a special case of being more stable than having only partially filled. Or only some paired up. So it makes sense that oxygen's ionization energy would go a little bit lower, because if it loses one, it then winds up with three. Winds up with 3p electrons all spinning in the same direction. So its ionization energy is a little bit lower than nitrogen's. See? Kind of nice. Questions? Now let me ask you this. Let's say I'm going to pull multiple electrons off of magnesium. I'm going to pull one off. I'm going to pull a second one off. I'm going to pull a third one off. What can you tell me about pulling that third electron off? Shaking your head like no. Right. It's going to be really hard because it's got the neon configuration after it loses two. So you wouldn't expect it to give one up. And when you look at the numbers, oh, heck, I picked one we didn't do, magnesium. That's all right. We could do beryllium. It pulls off the first one, 900. It about doubles to 1,800, right? And then look, 15,000. And these are in joules. Kilojoules per mole. So what you're seeing is pulling off the core electrons results in a huge jump in energy, which makes sense. So for something like aluminum has 3 valence electrons, right? It'll lose those first 3 pretty easily. The next one's going to be a bear to get off. Okay? That makes sense? So that's what that line is there, showing you where you start to remove core electrons. Arrange these in order. Argon, magnesium, phosphorus, in order of increasing first ionization energy. You always got to say first, so people know that's what you mean. So we want increasing. So the first one we're going to list has the lowest ionization energy. Which one is that? What's that? The lowest? Magnesium, right? But the one that's going to, this is the opposite of before, it's increasing. So magnesium is going to lose the electron easy. It's a metal on the left side of the periodic table, wants to get rid of electrons. Followed by phosphorus, followed by argon, which doesn't want to lose electrons. It's a noble gas with a complete octet. So read the question carefully. Last time we had, decreasing size in order of the largest was first, so largest to smallest. In this case, it's smallest ionization energy to largest ionization energy. So maybe that tripped you up. Questions? Okay, we're just about done. Then we can hit the review sheet. So electron affinity is one of these trends that is not as neat and tidy. And I will say the easy part of the trend is it pretty much increases as you go from left to right. Okay, up and down, it's a lot more erratic, as you can see. Say that again?
Grayson said that there's a question in the chat.
Oh, okay. I don't see one. Oh, is this only the case with 3D, or can it happen with? Oh, he answered already. Okay, thanks. Just saw that, Matthew. All right. So, going down, you can see, increases, but decreases there. Increases, decreases. So we're not going to try to explain all this and go through all that. Looking left to right, it's what you would expect. So the way this works now, once again, it's for a mole in the gas phase. The larger the money, I was going to say. The larger the number, the more it likes electrons, because it's energy given off, which means it's stabilizing. So fluorine, you would expect to have a large negative number, and it does because it likes electrons. So that makes total sense. The fluorine is the highest on the periodic table, and that the noble gases are positive, which means it takes energy, which means I can ionize a noble gas and make it an anion, but it's going to be in a controlled chamber, and I'm going to have to put energy in, and I'm not going to get anything out. I'm just going to put energy in. With something like fluorine, I'll put energy in, and then I'll get more out, and that's why you get a negative number. So it's giving off because it wants electrons, right? Once again, I'm not going to take the time to do it, but you can explain some of these trends again. Why the fact beryllium, right, is positive? Well, it's got the full subshell. It doesn't want an electron. You can do the same type of thing to start to explain these trends, just like we did with ionization energy. So you can read a little bit of that and just look at it. There is another chat now. And the noble gases will pretty much be positive. And a few other cases, you see these things happening, but oh, I guess that's just. All right. So that's the end of the material. Basics of electromagnetic radiation. Now, I've largely tested you that on the quiz. So, you know, I'm kind of done with that. You know, I mean, you'll see quantum theory stuff with electromagnetic radiation relating to Planck's equation and emission from transitions and wavelengths and frequencies related to that. That's fair game. But I'm not going to ask you, like, you know, which has longer waves, radio waves or X-rays, things like that. That was done on the quiz. I don't ask dates. Sometimes there'll be a multiple choice question that says, you know, what was Einstein's major contribution to quantum theory? And there'll be 5 choices down there. Occasionally you see something like that. So just be aware of what the major scientists did, but I don't stress that. Quantum numbers, of course, both what's valid or invalid, or what would be the quantum number designation for an electron in a, you know, 4th energy level in the S or something like that. You know, you could do the telling me the designation of an electron in a particular configuration. So what's the highest energy electron in, you know, the bromine atom? Okay, well, bromine's in group 4, so it have to be 4, and then P is higher than S, so it have to be a 4p electron. Right, so it'd be 4 for N, L would be 1 for P, and then ML could be whatever. Right, that doesn't matter what you assign that, and then the spin doesn't matter. Electron configurations, both of atoms and ions, isoelectronic, that type of thing, all that stuff, and then the periodic trends, size, ionization energy, and electron affinity.